Civilizations grow on energy, and the greatest power source in reach is the star we orbit. So what happens when we stop being children of Earth and become architects of the sun? And what kind of commerce emerges when entire solar systems start doing business with each other? What is a Dyson Swarm, and why build one? At a basic level, all of our power comes from the sun, and we use only a tiny portion of the massive amount that arrives on Earth. And yet that massive energy supply is but a tiny fraction of what the sun provides, not even a billionth. Once we came to realize that, we had scientists and futurists like Dyson, Kardashev, and Stapleton begin wondering if the inevitable fate of humanity, or any alien civilization, is to englobe their star in a sphere to use most of that energy. A Dyson Swarm is not a solid shell encasing the sun, like you might see in sci-fi for a Dyson sphere. It's a vast, growing forest of satellites, habitats, and energy collectors orbiting a star, each like a solar-powered leaf capturing sunlight. Individually, they are modest. Collectively, they can harness nearly all the energy our sun produces, over 100 trillion times more than we use today. And while more technology and raw materials always helps, we have the necessary technology and resources to build one even today. Indeed, I would argue we are already in the process of building one. But going from a handful of satellites and space stations to a proto-Dyson or a true full englobement from scratch is a long process, and one we detailed a couple months back. But having figured out how to build one, it seems like discussing life inside one is next. And the backbone of a civilization is its economy, and that economy is all about energy access and distribution. This is the hallmark of a Kardashev Type 2 civilization, or K2, a culture so massive it can capture and utilize the entire output of its home star, not through fantasy physics or singularities, but through scalable, modular engineering. Start with a few solar collectors in orbit, expand to asteroid mining and orbital habitats, and one day you've got a civilization of trillions basking in the light of a star fully encircled by human ingenuity. And that's where today's journey begins. We've talked before about how to build such a megastructure, but today we're going to talk about something more ambitious: how to live in it. From early industrial economies powered by orbital collectors to full-scale solar swarms supporting trillions, to interstellar networks of star-fed civilizations trading light and matter across the void, we will explore the rise of a Dyson economy. And we'll do it from the perspective of a classic baseline humanity. No AI overlords or hive minds here. Just ordinary people with extraordinary infrastructure, building wealth and prosperity on a scale we've never seen before. From scarcity to swarm, the early Dyson economy. Every great economy starts small, even one destined to span the sun. In the earliest stages of building a Dyson swarm, the economy is still tethered to Earth. But even at this point, we are already laying the groundwork for stellar-scale industry. While general ISRU, in situ resource utilization and space mining, will pave the way for space development, and possibly bring precious metals to Earth, the first real Dyson dollars, so to speak, are probably earned through space-based solar power, enabling clean and continuous energy far beyond what ground-based solar arrays can offer. And once you've got one satellite doing that, you build 2, then 10, then 100, then 100 million. Each collector multiplies the power available to expand further, and so the process bootstraps itself. The more you build, the more energy and capital you have to build the next wave. This is the spark of an early Dyson economy, a civilization no longer constrained by planetary boundaries, but still very much shaped by scarcity and logistics. It is also one that is not a product of government subsidy the way a lot of early space expansion would be. Space exploration and science research are definitely valuable and worthy long-term investments for civilizations, and money flowing into that helps develop the emerging solar economy too, but a nice, fungible source of power that can be beamed down anywhere, any time of the day or any type of weather is an economist's dream come true. Much of the early infrastructure comes from near-Earth sources: lunar regolith, near-Earth asteroids, even Martian moons, which can supply the raw materials for early orbital infrastructure of Mars, and the basis for our first interplanetary economy. These are our quarries. Mercury in particular is a tempting candidate, close to the sun, rich in metals, and already soaking in solar power. Its role as a raw materials hub could define an early phase of swarm development, feeding factories in orbit or on the moon that churn out kilometer-wide panels and power beaming stations. And then there's the planetary swarm, a miniature Dyson swarm built within Earth's gravitational dominance, or heliosphere. This includes geostationary orbit, Lagrange points, and the orbital neighborhood out to about 1 million miles. This volume alone receives enough sunlight to support the living space of tens of thousands of Earths, if filled with habitats and collectors. It's the perfect sandbox for early megastructure engineering. As the swarm grows, it begins to support more than just Earth. You're not just using sunlight to make electricity anymore, to run smelters or beam to Earth's power grid. You start using it for what we mostly use it for already: photosynthesis of plants to feed our food chain and biosphere. This is where all those space habitats we like to discuss here come into play, like the Stanford Torus and the O'Neill Cylinder. New living space for us, new land for life, new homes for humanity. Now, let me add a caveat here. It's very likely that a large portion of your energy in a Dyson economy goes toward computation and AI, and quite possibly all of it. Your civilization may have been taken over by machine minds in some Skynet or Matrix-style scenario, or you may have voluntarily migrated into virtual worlds, living as brains in jars fed on synthetic nutrient paste, or even as pure software, AI yourself, or some other post-human form. That's a perfectly plausible future, and one that diverges dramatically from a civilization composed of baseline humans. But at the Dyson scale, these differences mostly affect population sizes and which resources are most critical or represent bottlenecks. In classic sci-fi, machine civilizations are often imagined as iron-heavy, and biological ones as carbon-based, but in practice, machines would still need a lot of carbon for materials like graphene, and especially for radiators. Graphite, for instance, is an excellent thermal conductor with high emissivity, perfect for shedding waste heat, which is just as important in a Dyson economy as harvesting energy in the first place. Machines might not require much nitrogen, and neither would a civilization of VR-dwelling brains know that. But if you want lush nature preserves, farms, or planetary-scale parks, you're going to need nitrogen in bulk. Conversely, machine minds might require far more rare earth elements than humans ever did. And beyond that, it's hard to speculate. Future discoveries might introduce entirely new materials with unknown feedstocks. Still, the basic structure remains: energy in, waste heat out, and a supply chain moving raw materials into finished products. Whether you're a classic human, a biomechanical hybrid, or planet-wide AI, the machinery of trade, industry, and logistics probably won't be conjured away by magic nanobots, or Star Trek-style replicators, or some other super 3D printer. As we've discussed before, that handwave tends to ignore some very real limitations that still make traditional industrial-scale manufacturing the most practical approach, even in a Dyson economy. Indeed, all the more so because as we begin creeping up the Kardashev scale, our intuitive approach to production has to start scaling up. To give you an idea, let's say we are in a modest baseline Dyson sphere, one with lots of space habitats running at a population density similar to Earth, and thus about 2 billion times our current population. That would be 16 quintillion people. If we assumed modern pencil usage and demand, with good forest management, you would need a quadrillion acres of forest whose primary purpose was pencil production. That's only about 3 square feet or 1/4 of a square meter per person for pencil growth, and that woodland can serve a lot of other purposes simultaneously. We're just sustainably harvesting it for lumber to be used for pencils. But at the Kardashev 2 scale, that means 8,000 to 27,000 Earth's worth of space habitats are devoted to this system-wide, depending on your land-to-sea ratio, or about 6 billion O'Neill cylinders or 5.5 trillion Stanford toruses. And needless to say, that's not going to all be in one place. There's not much of a supply chain on a pencil, assuming we even use them much in the future. There is no giant swarm of oversized McKendree cylinders or Banks orbitals just growing trees to be dumped into the one and only solar mega pencil factory, but it is also unlikely every O'Neill cylinder, let alone one Stanford torus, has its own pencil factory. Even an economy only a bit more automated than our own, and you need a lot of automation to build Dyson swarms, isn't going to need much more than one person in a million making pencils, so it's a lot more likely than some localized habitat swarms of a few hundred O'Neill cylinders and a few thousand smaller habitats and facilities like the Stanford Torus that comfortably house a population parallel to the US or EU, that there's a handful of pencil factories there and they grow or buy wood wherever it's cheapest and easiest. Space freighters and trade in a Dyson. You're probably thinking by now this is a weird example, mountains of pencils in space, and that is intentional. I like using the weird ones, because when you're working with Kardashev scale thinking, the ordinary tends to break down. We explore this idea in our Cosmic Capitals episode, where we worked out how many full-time coffee machine repairmen would be needed to service just one minor government office in a K2 civilization. Realizing it would number in the tens of thousands, all serving under the local coffee master general. Our brains simply are not wired for this kind of scale, and science fiction writers often struggle with it too. Ironically, one of the few franchises that gets this even vaguely right is the deeply dystopian and wonderfully absurd Warhammer 40,000. That setting occasionally runs the math on what an empire of a million worlds looks like, complete with hive cities devoted entirely to shuffling paperwork. But even that is still 1,000 times smaller than a Dyson Swarm economy, which concentrates all that complexity and population into a volume just a few hundred million miles across, not stretched across light years like an interstellar empire. And that's a crucial point to understand. A Dyson Swarm isn't likely to be homogeneous. It won't be a uniform shell of identical habitats neatly spaced around the sun. It's more like an archipelago of thousands or millions of clumps and clusters, conglomerations of habitats, farms, factories, and infrastructure in varying densities and orbits. You might have rung worlds, giant linked chains of habitats, or megastructures tethered together, while some habitats might exist nearly in isolation, connected only by beam relays or occasional transport runs. And because plants don't need full sunlight, or in some cases even visible light, you're likely to see agricultural zones pushed further out from the star, soaking a redder, more infrared-rich spectrum, left over from the inner regions sipping heavier from the classic visible and emitting it as infrared waste heat. The closer zones we bathed in a blinding level of sunlight, heavier in blue and UV radiation, ideal for industrial power stations or machines, but not great for greenery or long-term habitation, while space habitats will want to remove most of the main UV and infrared to receive a mostly visible spectrum, and will bounce those unused wavelengths back out and add them to its own waste in the further infrared zone. This gives the swarm a kind of vertical structure, with down being toward the sun, and each level or layer having not just a different intensity of sunlight, but a somewhat different composition of light and other radiation, influencing the default purposes of facilities, light ecology, and optimal use of what's there at a particular place in the wider swarm. Now, let's talk about freighters for getting between places in the swarm, because you're not going to haul those pencils and lumber and nutrient paste in your backpack. One of the strangest economic realities of Dyson Swarm is how cheap transport can become. We think of space as insanely huge and empty, and it is, even just this region within a couple AU of our sun, but it can be deceptive in the context of a Dyson. In the microgravity vacuum of space, a freighter moving between two habitats in the same orbital cluster might require almost no fuel at all, just a nudge and a bit of time. There's no fuel spent cruising, just speeding up and slowing down. And even habitats tens of thousands of miles apart could transfer cargo more efficiently than two towns separated by a mountain range back on Earth, and the energy needed to accelerate a kilometer per second to get you across a bigger volume than a planet in under a day is actually quite small compared to the gas needed to drive a car across a continent. That means trade, even bulk trade, is viable at scales we would not expect. A habitat producing food, lumber, or metals might regularly ship those goods to dozens of others across the swarm, not just to its immediate neighbors. The vast majority of that cargo likely isn't going from one side of the swarm to the other, it's more regional. But even so, it allows for a remarkable degree of specialization. One cluster of O'Neill cylinders might focus on agriculture, another on precision manufacturing, a third on AI training servers, and so on. You might even have full logistical hubs, dedicated habitats or platforms functioning like the warehouse districts or port cities of old. For context, Dyson swarms are generally spread out. While you could pack them into a dense, thin shell around a star, that's not an optimal setup for maintaining safe, stable orbits. On the other hand, there's little benefit to evenly distributing everything across a huge volume either. The common visual shorthand is a shell of land encasing a star, but that does not work. Not only is it mechanically unstable, but such a shell would still give you perpetual noontime equatorial sunlight, which is not ideal for most living conditions. To get a more useful spectrum and thermal range, you'd actually want the average radius of the swarm to be more like 150 to 200% of Earth's distance from the Sun, and since all our living space will be in rotating habitats anyway, the exact placement isn't too concerning. What does matter is light capture. If we fill the volume between Earth's aphelion and perihelion, roughly a 5 million kilometer variation, with O'Neill cylinders spaced several hundred miles apart, we could effectively absorb all the usable sunlight. You might very well want a much wider volume, and you would expect a Dyson Swarm to vary in density by radius, with things falling off but never stopping, likely all the way out past the Kuiper Belt, or where the Kuiper Belt was before you mined it out to make a Dyson. There's no real need to space everything evenly either. Certain industries benefit from being much closer to the Sun, and others can thrive farther out, and you are more likely to see thick clouds of habitats floating in patches with big gaps rather than an evenly distributed fog. Vast archipelagos of habitats, tight clusters with wide gaps in between. These clusters would vary wildly in size and distance. The same super-strong tether that permits a space elevator tens of thousands of miles long in Earth gravity permits one millions of miles long in microgravity, and even more mundane materials permit plant-sized conglomerations. As long as you lash things together with tethers, you can have physically connected conglomerates spanning light seconds. Some of these might be just a few habitats and solar arrays, others could grow the size of a gas giant, linked megastructures containing thousands of Earth equivalents in surface area and housing hundreds of trillions. And within these megaclusters, inter-habitat trade would be far easier and faster than shipping cargo between two cities on Earth. In such a setup, you could have a bulk freighter hauling 1 billion tons of lumber each day to the No. 2 Pencil Habitat Factory, while dozens, maybe hundreds of smaller ships, from Millennium Falcon-sized couriers to full-blown container vessels, move goods in and out. Mean would come from vast microgravity warehouses, while larger high-speed freighters run routes between these constellations of habitats, scattered throughout the wider solar system carrying luxury goods or bulk materials that were cheaper elsewhere, like deuterium from Neptune. Megafreighters as mobile habitats. That doesn't mean you'll likely see gigantic torch ships blazing across the Dyson to deliver bananas. Most of the bulk transport will be slow, steady, and carefully timed. Think orbital tugs, magnetic rail launches, solar sails, or even power beam assisted gliders coasting between habitats. At the Dyson scale, overnight delivery exists inside these clusters, which again might have clusters individually much larger than Earth in living area and population, to slow megafreighters that promise delivery inside a decade, but that's fine when your cargo is 2 gigatons of ice for an O'Neill cylinder being commissioned, and your megafreighter, while mostly automated, has a crew of 1,000 who live in their own Stanford Taurus, during their 20-year, low-energy orbit out to the icy moon they call a hometown. In space, delta V is more important than actual distance, but in the same vein, time is money. Money spent on crews, money spent on servicing spaceships, money lost that a ship could have been making if it delivered its cargo twice as fast. Now that's an interesting dynamic too, since that ship is probably a more or less self-sufficient habitat that imports luxuries at a premium and pays for them with its own cargo, about 2 gigatons of ice, which, for context, is roughly half a cubic mile of water, or 2 cubic kilometers. Odds are it's a mostly automated vessel, and the main reason to have a big crew aboard is to keep people sane and socially stable, and maybe repel the occasional ice pirate boarding party. Everybody else has got a normal day job doing whatever most of the rest of humanity is doing. The level of automation required for Dyson swarms tends to imply a fairly short work week for subsistence. I would say the typical person only needs to work an hour a week, except that only functions if we assume the same standard of living as now. A civilization with more wants and needs to be filled needs more work done than our current one, seeing as we tend to have way more stuff than our great-grandparents had, and our work week is overall a shorter and lighter one than theirs, as we're just vastly more productive due to modern technology. My personal guess is that the work week for the average person never drops below 20 or so hours a week as you start running into existential purposelessness and stir craziness. So if that level supports every average family in a mansion, or even several thousand acres of garden park per family in a rotating habitat, then that's where things land. Back to our freighter. You probably have smaller ships docking with it along the journey, and entire families being raised on board who disembark when it reaches its destination, or hop over to some trader pulling alongside to sell pencils to the crew, paid for against their credit line, backed by all that water. Maybe the crew all own shares in the Triton Ice Mining Company, which itself might operate a few thousand of these megafreighters. For context, if you need one such shipment to fill the water supply of an O'Neill cylinder, and wanted to build a Dyson Swarm over 10,000 years reaching just 10% light capture efficiency via habitats, you need around 400 trillion cylinders, or about 40 billion built per year. That implies nearly 1 trillion megafreighters hauling water at any given time, with 1,000 of them arriving every second. So a company wanting to issue weekly paychecks to its employees might only need 1,000 such freighters, and in doing so, it would still own just 1/billionth of the freighter fleet in the interstellar ice mining industry. And remember, each of these ships would displace more mass than every vessel in every navy on Earth combined. You can obviously build slower or scarcer. Maybe you spend 1,000,000 years building to a 10% habitat Dyson, but even here you still have got 10 of these megafreighters arriving every second. Or maybe just build them 1,000 times bigger to justify the cost of a crew that size. You got this for every commodity and at every scale too. The family shipping business between two hab clusters might be their extended family too, and have its own habitation ring, while the grain barges running between rung worlds of Terra might form something like a bike chain civilization of 10 billion freighters, each home to tens of thousands of people, where 1/10 of the population works on overseeing and maintaining the vast mills that process that grain into flour during the journey. Again, the scale is simply huge. As we think about civilizations building megastructures and economies spanning entire stars, it's worth remembering that every great system starts by protecting its foundation. For us, that foundation is our digital world, and private internet access VPN helps you safeguard it. A VPN works like the scaffolding of a Dyson Swarm, invisible but essential. Without it, your internet traffic is out in the open, vulnerable to hackers, advertisers, and ISPs. With PIA, your data travels through an encrypted tunnel, safe from prying eyes. I've trusted PIA for nearly a decade, using it daily to keep my information secure. It's quick to connect, and with servers in 91 countries and all 50 US states, it lets me access content and services no matter where I am. Plus, one subscription protects every device in my home, from laptops to phones to tablets. So if you want to keep your digital economy as secure as the Dyson Sphere, check out piavpn.com/IsaacArthur for a huge 83% off, just $2.03 a month, plus 4 months free, and it's backed by their 30-day money-back guarantee. Interstellar trade. This can include interstellar shipping too. There isn't much you need to move between star systems, relatively speaking. When we're talking about Cartership 2 civilizations, relatively can still mean staggering scale. Maybe there's a planet around Tau Ceti whose northern continent produces a wine famed across the stars. They ship 50 billion bottles back to Earth and the solar system each year, and with a population in the quintillions, it only takes 1 billion people deciding to try it to make that a viable trade route. There are only 8 billion people on Earth, so if you imagine something only 8 people might enjoy doing, that could still mean billions doing it in a Dyson Swarm. As we noted in our episode, building a Dyson Swarm from scratch, if you are shipping durable goods like metals, volatiles, or basic elements between star systems, you could bring in an Earth's mass worth every 10,000 years using just a sliver of the sun's energy, assuming you're fine with speeds under 1% of light. And if you want faster shipping for premium goods, you might be moving many trillions of tons of material a day. Even if that works out to just a pound of interstellar goods per person per year, in a civilization of a quintillion, that still means thousands of Star Destroyer-sized ships arriving daily, each one offloading goods and onboarding fresh crews for the next leg of a century-long return voyage. Currency, capital, and control in a Dyson economy. In a civilization where energy rains from the sky at 1 trillion times our current consumption, it might seem like money would become obsolete. But money isn't about scarcity of power, it's about scarcity of coordination. Even a Dyson Swarm, maybe especially in such a vast civilization, people still want different things, at different times, in different places, and someone still has to build, maintain, deliver, insure, and manage it all. That's where currency remains useful, not to buy raw sunlight, but to allocate time, labor, and specialized resources. You will still have miners and machinists, coders and chefs, artists and arbitrators. Banking might stretch from cluster to cluster with high latency smart contracts and slow but secure inter-orbit verification. Reputation systems and ledgers might matter more than fiat. A bad review might echo across millions of habitats faster than a court summons ever could. It could be a commodity currency. That's what gold and silver coinage are. This token may be exchanged for 1 ton of deuterium, or 10 tons of aluminum, or 1 billion joules of energy. I would tend to bet that fiat currencies would remain the norm, where a government or large entity simply says this token is money, and the commodity backing it is basically trust that they will still exist tomorrow and honor that token, which is generally a measure of how large and stable the economy in question is, and how many guns it has to ensure it stays that way and can protect its property and assets, or its citizens and allies. Or you could have several million different currencies in a system this size: commodity, fiat, hybrids, crypto, or something altogether new. Banking has issues with light speed lag, so each major habitat cluster might use their own internal currency that was near instant, while larger payments processed more slowly and had conversion fees. Light lag inside a star system is not a fatal issue for banking though. As a reminder, banking arose when trade between cities took weeks, and even throughout the 20th century, interstate and international banking often had multi-day delays, so a few hours of light lag between Pluto and the Martian swarms is not likely to be impossible to manage. Selling property between star systems might be harder, and we've looked at that in other episodes, and I think commodity or trust and reputation focused currency becomes more probable there. Intellectual property, particularly a high-tech civilization where software, simulations, and design files can be shared system-wide in seconds, may become one of the most valuable exports. A single viral invention or popular game could be worth more than a moon's worth of nickel. Expect patent empires, open-source megacores, and idea piracy on scales never before imagined. We don't tend to think of IP theft as violent, but in a Kardashev-scale civilization, cyberpunk tropes can become daily realities and need to be upscaled to the population. Picture mercenary squads launching assaults on continent-sized research facilities to steal a prototype or algorithm, and only registers as a minor news item in the source system newsfeed that evening. Of course, in a Dyson Swarm, there's no universal day or evening either. Earth doesn't even have one in a strict sense. Still, it is easy to imagine many systems defaulting to a 24-hour clock synced to Greenwich, or perhaps choosing some symbolic epoch instead, like counting in megaseconds from the first moon landing. A megasecond is roughly 12 days for reference. Timekeeping would likely remain uniform within each habitat cluster or orbital conglomeration, but you might find neighboring swarms keeping time in 100-hour days with 100-day years, while others mark the passage of time by the shadow of a ceremonial sundial spinning in microgravity. Language and units of measure would be similarly varied. There would probably be an AI standard tongue, loosely derived from English I guess, used by machines to translate between local dialects. The metric system or some evolution of SI units would likely dominate engineering and trade, yet the spoken languages of humanity might drift and diverge into new forms, each unique to its habitat, long after anything recognizable from modern Earth has faded into obscurity, remembered only by archivists and androids. And what about land? In space, land is manufactured, but that does not mean it's free. Orbital real estate, prime zones near the sun, near trade routes, or near cultural hubs will be as hotly contested as property in Manhattan or Tokyo. Who owns what becomes a question of who built it, who maintains it, or who controls the drones currently stationed on it. It's easy to imagine aristocracies of habitat owners leasing land and power access in return for services, or microstates forming as habitat clusters, backed by reputation tokens, or even energy-backed currency. See our episode on space feudalism for more on that. The endgame. Dyson economies in the galactic context. And where does it all go? When you filled your solar system with trillions of habitats and quadrillions of minds, what comes next? Expansion. A fully mature Dyson Swarm doesn't sit idle. Long before it gets anywhere near K2, it beams out colony ships, spreads industrial probes, and seeds future swarms. The interstellar frontier becomes the greatest economic bet of all time. Not just a new market, but a whole new sun to industrialize, and 100 billion of them lie before us. This brings us to the notion of fleet economies, effectively moving worlds, ships and habitats large enough to be cities or nations, traveling between stars, individually or in swarms themselves, generating wealth en route via trade, data, or simply transporting goods or people to where they're needed centuries from now. You might get stellar pacts, trade agreements between star systems, or even between clades of civilizations, exchanging designs, music, data, biological samples, or even entire ecosystems. And just as with earthly empires, you could have inter-Dyson wars, economic, ideological, or actual kinetic conflicts between stars or between megastructural coalitions. There are risks. Economic systems this massive could become fragile in unfamiliar ways. Supply chain collapses that ripple across a light year, runaway automation that leads to economic singularity or stagnation, or overdependence on simulations leading to cultural decay. And then there's the philosophy of it, when every person could feasibly own a continent or even a planet, depending on how thin they'd like to slice the pie, when lifespan is effectively unlimited and the energy needs are trivial, what drives innovation, desire, and purpose? Perhaps legacy becomes the ultimate currency, not just building wealth for your children or even your nation, but for the galaxy. You find a project that takes 1,000,000 years to complete. You donate 1 trillion tons of ice to green a planet you will never see. You create a symphony that plays across orbiting speakers for centuries, echoing from ring to ring, or beam signals to other galaxies, and fund the modelers who will listen for replies 5 million years later, hoping to hear from alien life. When your economy is driven by the stars themselves, stellar ambitions are on the table, and when you manufacture whole worlds, the sky is certainly not the limit.